Right, I'm going to continue again. So welcome back. So today I hope to sort of finish most of the basic setup of superselection structure. So we will try to find this category. We'll see how far we get. But the thing that we basically were working on yesterday is finding a lot of products on the set of superselection sectors. So I had this superselection criterion that would pick out a set of interesting representations, and we wanted to find a monoidal product on this representation, and the monoidal product should be one that's kind of like a physically relevant one. So that will be the fusion in this solution. Good. So just let me recall what my example was that we are going to build already. So we have a star algebra, Zeta algebra, we get the endomorphisms of this, and then I define monoidal products on the endomorphisms just by opposition. And these were the intertwiners intertwining the endomorphisms, and the monoidal products on these were defined like this. Good. Then I had this category delta DHR. So my first definition that I gave yesterday, I gave was slightly better than today. But yesterday I looked at endomorphisms that are localized and transportable. And we want to define a simple monoidal product on this. But the issue that we had is that the intertwiners in this category, they are no longer in general inside this algebra A, or rather in some bigger algebras, some big closure. So this means that this expression here may not be defined. Good. And more generally, so I constructed these maps that's supposed to be the anyons, and the way I constructed them, there were automorphisms of this A. But if you want to go the other way, and they satisfy subtraction criteria, but if you want to go the other way around, so you start with the representation satisfying the criterion, you don't quite get an endomorphism of A, but you get a map that maps A into a slightly bigger algebra than into this algebra. Right, so we need to, so the main idea is going to be, well, we need to extend our maps to a slightly bigger algebra that, first of all, that contains the image of all these representations, and second of all, it should contain these intertwiners. So that's the first step I'm going to do. So this one I call the auxiliary algebra. Yeah, I will not say it now. But yeah, so that's what I just said. We need to make sense of V, where V is in this von Neumann algebra. So again, I will often drop a symbol by 0. Hopefully it's not confusing. So we want to extend our morphs or endomorphisms to some bigger algebra that does contain these things. So the way to do is we choose a forbidden direction. So basically what we choose kind of a cone in a certain direction. Doesn't matter which direction you choose. And then, well, we can think of these, we can define a set. Right, so yeah, this, so we can specify the cone up to the apex by this angle. This is the direction in which it points. So if you think of the cone at the origin, this direction, if you translate it to the origin, then theta is going to be the angle of the middle line. And then phi is going to be 2 times the origin in the points. 1 times whatever you find. But that's so that's how I can have the cone, and what I'm going to do is I look at the set C theta phi, and all the cones that if I would translate them to the origin, they would point in a different direction, so they would not intersect with my given cone. Right. So that's always a translation. So when I compare the 2 cones, I can always translate them first to the origin, and then I compare the ends. Right. If you do this, you can show that this is a direct set. And if I take the union of all these kind of cones, I get part 2. So I mean, sorry, I want to introduce a picture here. But as I said, I am allowed to move the cones So I think it should be more on here. So this is my forbidden cone. I hope you can see this, and it's not only something you can see here. But yeah, you can, for example, a cone like this would be in a different direction. If they translate these things, you get.
I have a quick question.
Yes.
So, when I realized when I was working with this, it seems like you don't need to like thicken the forbidden direction at all. Like if you could say, oh, you want cones whose angles do not intersect the ray at angle theta, or like that direction. It's like, is there a good reason for wanting to thicken it?
I mean, there's different ways of doing it, yeah. So you don't really need to think of a cone. You just you just need one. So in this setting, you just want basically what you want is that you cannot sort of rotate the cone all the way around without going to a certain direction. So that's really the way you're thinking of them. But yeah, there are other alternative cones that don't need this forbidden cone. I'll mention some later. But yeah, there's many ways of doing this. You just want to kind of cut out the parts so you can install the system.
So thank you.
Yeah. Right, so now we define an auxiliary algebra in this way here. So I just take the union of all these cone algebras. I take the weak closure, so I get a normal algebra, and I take the closure in the C-star image. So this is now a nice C-star algebra, and it does contain the simple triangles, as long as, of course, we not pass this integration. Right, but yeah, the important part here is that this is a directed set. So we there's the inclusion of these cones, and you can always find a bigger one that contains two of them. And that's of course very nice, because these kind of C-star algebras, it basically means it's enough to specify things on these cone algebras, and then as long as things are compatible, we can extend it to the whole C-star. That's kind of going to be the end. Right, and because of this property here, it's easy to see that actually our original algebra is a subalgebra. Right. Maybe I should point out at this point that I was talking this symbol by zero representation, but of course taking this closure, this depends on which representation you're in. So this algebra depends on the choice of the references. Good. So that's our auxiliary algebra. It's mainly going to be a technical tool. I'm not going to say this all the time, and of course we have to make a choice here of one direction. Choose a different direction, you will get the same thing. It's not so difficult to see. You get this property intersection. So right. But this is the main sort of technical point. So suppose we have this representation that's localized and transportable. So localized again, it means that outside of some fixed cone, it's equivalent to the vacuum representation, the reference representation, and I can move this cone around. If I use a different cone, I find something unitary here, that's localized. So suppose you have such a representation, then we can extend it to a star homomorphism of this auxiliary algebra to itself. Right, so this I will denote this with the string A. And more importantly for us, this extension is actually we operate continuous on these algebras. So it doesn't matter too much for us what this weak operated topology is. If you're not familiar with it, it's one of the sort of natural topologies. Right. Good, so that's very nice. Let me briefly sketch the proof. So you take some cone, and you choose another cone, disjoint from that. Then by localizability, I can transport this row to something that's localized. Yeah. So I assume that you do. So this means there's a unitary V such that this is true, right? But then if A is in my cone, then rho of A is by definition a unitary representation, but by recognizability, this is equal to pi 0 of B. So on any given cone, my representation will always look like conjugation with some unitary. Right. So conjugation with a unitary, this is continuous in the weak operator topology. So this means I can extend this whole thing to the weak codes with this algebra, this one, so that's besides this one. And yeah, so this is compatible with this directed structure that I mentioned. So it's inclusion into the Topological set. So this means you can define it from all these cone algebras and then extend it. So that's the idea. So it's really the point of this whole superselection continuum is that when you look at just at a single cone, it's always very simple. Of course, this V is going to depend on the choice of cone, and this is not going to hold for all A. If you choose A with a different cone, you might have to use it. Good. So that's sort of the main technical tool. And now we solved our problem.
One question.
Yes.
It all depends on background.
So this specific thing does not depend on Algebras, I think. But what does depend on Algebras is the point. Yeah. No, it actually does depend on Algebras because you need Algebras to show that this thing actually ends up. That's the thing. Yes. If you don't have arguability, in many cases you can, like in a Topological, you can explicitly construct representation by this two-by structure. But then you cannot show that anything satisfies the things with you. Good. So yeah, so I mentioned this arguability. It's actually, you don't need quite arguability, you can have something weaker. I would, well, it's not anything. Good, so that's the auxiliary algebra. So I already mentioned the first thing, so I'm going to define this category, and it doesn't depend on the choice of this algebra, this forbidding direction. If you're working with, formal nets for the circle, for example, this technique of choosing like a forbidden direction is very much like you point to the circles to get right. In the on a circle you have the same thing the same issue that the set of kind of interval that they don't form the direct set. Point to the circles. There's some other approaches, so you can do universal algebra, you can do kind of like coordinate charts approach where you make this different forbidden directions for the different parts of the system, and then make sure that the overlaps they coincide. Coordinate charts and manifolds. So my colleague Alex Schenkel will talk about sort of more geometric approach to the vectorization algebras next week. Or you can just look at nets of representations of the codes and it's satisfying certain compatibility conditions. That's like Gabriel Verbeek and very recently in axiomatic approach. Function. Good. So that's just some comments. So let me now give a new definition of my DHR category. That's the sort of problem that I had before. So what are going to be objects now? The objects are going to be star homomorphisms from A into this auxiliary algebra. And well, really we want to see A as embedded in this thing. So which are localized. So there's some that's what I just said. So there's some cone lambda such that so then the outside that and transportable so they can move the organization. Right. So instead of star homomorphs from A into this algebra, I could have just took the endomorphisms from the auxiliary algebra to the auxiliary algebra. That would amount to the same thing. But maybe from a physical point of view, we only really care what we do. algebra represents. Good. So yeah, and then the morphs are the same as before, so the finds. Right. Of course, the main point now is that what I showed you last time using hardware reality, we can actually show that these twiners are in this auxiliary algebra. That's the point. Just to reiterate, it's the same as I said earlier. This category very strongly depends on the choice you find. Precisely to this issue. Sorry, this is. Right, so now we can define a tensor product. It's almost exactly the same as before. Only now, instead of my original map, I have to take the extension. So the first thing you saw is that this is a map by definition now from A into the auxiliary algebra. So if I want to compose this with this map, I need something that's actually the auxiliary algebra. So you see the extension. And similarly, we can now define the monoidal intertwiners like this. And this is now all well defined, and you can check that it's so guys. Check. And with this definition, the category is a monoidal category. Good. So that's just to verify conditions. It's the same calculation. Now I agree. And of course, the tensor unit is going to be the identity, which I will use the iota, and that's the vacuum sector of the trivial sector. I often call it vacuum sector, but people doing the quantum field theory or relativistic space-time, they should say vacuum sector because there's no action of the right. Let's that's the trivial sector. Good. So yeah, so there's many physical interpretations, and maybe that's a good point to mention now. So how can they think of these kind of maps? Well, the way in the example they constructed, what they did is they created an excitation in our system with this. So this composition here really just means first I create this excitation sigma, and then I create another excitation from. And now I have two excitations. Right. So this is what's sometimes called fusion in the physics literature, or maybe more precisely, what they usually meant there. So we can now look at combining these two excitations, and we can see can we maybe decompose it into kind of like simple units. Let's see, bring two charges together, and something like that. So I will come to that later. But yeah, this is the tensor product. Good. Right. So what I said earlier, so sort of one of the main achievements of this DHR approach, which is basically what I'm trying to do here in our setting, is that it naturally leads to a braiding system. So the braiding is again so we heard a little bit about this yesterday also in website talk. So you can think of two of these animals here, and I can move one along the other. It goes back to its original place, and I want to know, what happens to my system. Good. So what is that for braiding? Well, you can think of sort of this picture. You have a 2D plane. You can look at time going from let's say from the bottom to the top. And you can see the world rounds that traced out by these things, and you see obviously these braids appearing. On this picture, you can already imagine that's a topological feature that's going behind might be going in front. So that's what we're trying to capture. Right, so how do we formulate this mathematically? So what's a braiding? So if we have a monoidal category, then a braiding is a family of natural isomorphisms. So for each pair of objects that relates A tensor B with B tensor A, such that some diagrams compute. And I'm going to show this diagram on the next slide. So I want to first introduce terminology. So this is called a symmetry. If I do this interchange these two particles twice, if this is identity operation, so that's what you would guess, for example, if you have both interchange them twice, well, like we have. Right, so you have a braiding, and then of course you have a functor for one category, from one braided category to another braided category. You want this functor to preserve the braiding. You can define this in the obvious way. I'm not going to do that here because I don't really need that. Maybe some examples to keep in mind. Category vector spaces within your maps, where the tensor product is the usual tensor product, and then the braiding is just flipping the two tensor factors. That's kind of like a trivial one. So this is a symmetric category. So it's symmetry. Flip twice, you're back to start with. Maybe slightly more interesting, and we will see this later. If you take quasi-triangular Hopf algebra, I think that's enough, but I don't expect that, but I think that's enough. If you look at the representation category and using this quasi-triangular property, you can define a braid. I see some people nodding yes here, so got it right here. Good. So this will be sort of the example. But yeah, this is the properly braiding. Good. So yeah, I said my braiding should satisfy some axioms. These are the natural ones. Right. So this is in general case. So in the non-strict category case, so I can mark X different bases, so that's these maps. So ignore them for now. But the point is, if we have A tensor B tensor C, and I want to go to B tensor A tensor C, I can by swapping the factors, I can do it in the two different ways, and of course I should get the same thing. That's yeah. I mean, if I just change the diagram, I can see this one, and the same thing should hold for the inputs. Good. Right, so if you have this thing, you get the representation. Good, so we want to define a braiding. So let's go back to our sort of toy example. So I changed my notation slightly here, but I just mean the animals of algebra A. So what would it mean to have a braiding in here? Well, we would need to have some intertwinement between rho composed of sigma composed of rho. Well, if you take these two arbitrary animals, in general, there's no reason why there should be intertwining between them. Typically, they will not exist. So we cannot define a braiding this scale. But on our category, we have much fewer objects in there, and now we can define the braiding. And we are going to use that our objects are localized and transportable. Good, and so maybe as a completion from the construction, this really works because of the sort of the geometric properties of these cones that I have. So there's kind of like enough space, and that's nothing. So you can do like a very careful analysis that maybe make this geometric picture much more explicit. Right, so yeah, about this next thing. So yeah, can we first go with the construction, and then I will show this whole thing and the pictures maybe. Right, so what we have to do? Well, we take first two of these anamorphisms, the auxiliary algebra, localize the two cones, they all run their whole the sigma. And what I'm going to do is I'm going to choose a cone lambda hat to the left of lambda rho. Right, so I'm in two dimensions here, so I need to define what do I mean for one cone to be to the left of the other. So this I can use within direction. So basically you can think of which direction do I have to turn this, I can turn everything anti-clockwise, which yeah, then I can find what's going to be the left of this auxiliary cone. Right, I think that's much more clear in the picture. Right, but by properties of the category, I can find a sigma hat that's localized in this lambda hat that's unitarily equivalent to our sigma. So what it does is I have my sigma here, and I'm going to move it. Right. So now our localization, this row. Yeah. So yeah, I mean, even to the left and the row, I should say, let me say that explicitly. I really mean also with this joint. Right. So now our localization, because this row only acts non-trivially inside lambda row.
Can you draw a picture, maybe?
I will draw a picture on the next page. Yes, I appreciate this. Maybe a little bit difficult to follow this. I should probably done the other way around, but let me finish the construction. But the idea is that now my row and my sigma hat, they act not necessarily on different parts of the system. So that means that the composition of this map or this map, I can just interchange it to, because they are not going to be. So one will act as the identity, but the other acts. Yes.
Do you have control over if it's braiding that you get symmetric?
So when the grading is symmetric,
Do you know, can you identify the cases when it is symmetric, and is it in general symmetric or not?
so in our examples, it's not symmetric. It's actually the opposite of the very far end, but we will end up with a modular category. So in 2 dimensions, if you use cones, there's not much you can say about it if they will be symmetric or not. But if you would say, let's say, go to 3 dimensions, say you still use cones, then it's automatically going to be symmetric because I can always kind of move that around. Yeah, but it depends on the kind of localization region that you use. So if in 2D, for example, if you would use something like convex, something like that, like convexly supported, it would be symmetric. Okay. Right. But yeah, the point is I can interchange these two things. So these are now equal to each other. And then I can just move the thing back again. And then I end up where I want to be. So this is how I define my grading. Again, I'll show the picture soon. So I first move this one to the other way. I can interchange the two, and then I go the opposite. And then if you look back at our definition, this is the operator that you get, and you'll see it's right. So of course I had to make some choices here. I had to choose this cone lambda sigma, and I have to choose an intertwiner there, might be more than one. But it turns out that this operator that you get here, it does not depend. So the only choice where it does depend on is that if I move to the left or to the right, I could equally move things away to the right. If you do move it to the right, you get a different grading, but it's related to this one. This is basically the inverse. Good. So here's the promised picture. We start with two objects, and the rho and the sigma. Here, I'm going to choose my lambda sigma hat. I use my hat multiplication, but it should be a local lambda here. So I move it out of the way. So this here, rotate that thing to the left, that is out of the way there. And so I can map with the unitary from this moves to this one with this unitary. And that's just row 3 right into the definition. Good. So at this point, because I act on different parts, by locality, I can just interchange these two things. So this one is actually equal to this one. And now I can move thing V star. So from the definition, it's obvious that V star will move everything back. And so I'm back. So these two columns are the same as these. My picture was right. But now I am in the opposite order. So that's how I define the grading. So I really need here that I can move these things away and that I can interchange. Good. So hopefully that helps with the picture. Right, so maybe I should say this at this point, so you can see that it doesn't depend on choice, so basically it's kind of like a deformation argument, so you can move these things in steps that in these cones are there's steps where cones are sort of nested with each other, and you can see that they are same. And from that argument, you will also see that if you do it the other way around, you can sort of continuously from one and right, so we get our braided now. And of course, we have, for example, of the Torah code. So, you know, the question is, natural question is now, can we actually calculate what the braiding is going to be in case of the Torah code? The answer is yes. And that's what we can use here is, well, we really have this explicit description of these intertwinings. I had these parts moving one back to the other, so I'll show a picture again soon. But yeah, the point is we had for these intertwiners V, we could construct a very explicit sequence and conversion is combined. So that's so yeah. So if you look back at the definition of the braiding, the main thing that we have to calculate is this row braiding. So actually here in the definition, actually the A is there now. Yeah. So if you want to calculate what this thing is going to be for our different centers. Good. So we've seen before. I actually gave you the argument that we have this convergence in the strong operator topology. You can also show that the convergence in the weak operator topology, the same kind of things. But yeah, the important point is with our lemma, this map is weak operator continuous on this cone algebras. And these VNs, they are in my cone algebra. And this agreement is also in there because that's the most in the weak operator topology. So I can calculate by continuity, I can calculate rho A and V as the elements of these things. So now I'm in business because these were algebras in our things in our C style. So these were local observables that I had before. They were just these parts. So I can compute this explicitly. And what you get in the case of the Torah code is that you always get plus or minus V. So the sign depends on the relative position of the two things that you move and of the type of points, essentially. So let me show that again in the picture. So we have a row, let's say it's one of these X-type springs, and this is one of these Z-type springs. So what do I have to do? I had to choose a different cone and I move this over there. And how could I construct this map here? Well, I can take the element of the operators that go like this. I go there, I go along this bridge here and back here. So these are my Vn, and then every step, and I go a little bit further out. So that's going to be my V is going to be a limit of these kind of operators. So my rho of V, or rather rho A of V, is the limit of rho this F psi n. So that's really this map, this part here. Right. So this one is defined in terms of so this is now local operators. This rho was defined by conjugation with one of these part operators. So if I just use my path to organ so that it's out there. This in the Torah code, these things are either all sigma x's or all sigma z's. So I just have to check. I can easily commute these things through. So I either get plus sign or minus sign depending on input types. So in this case, of course, I made it so that there's only one crossing. They cross that multiple times. You have to be a bit more careful, but you can always arrange it in such a way because everything only depends on the inputs. You can always move them out to the playlist. But yeah, so in the end, it's really boils down to this simple commutation problem. The problem is. Good. So what do we get then? In the toward code. So these are the types for the particles. This is the braiding for these two things, and I always get plus or minus the identity. And the sign depends, so this plus minus here depends on so the relative position here to the right or to the left. But this is basically the table. But in particular, what we see if you have an X particle and a Z particle, and we interchange them. So interchange them twice is the same as putting one around the other. I get minus the identity. That means they have these values. Right, so that's the iteratory code, and this is the answer that it should be. So that's really good. Right, so I have so I think it's enough. Right, so that's the braiding. So I want to talk a bit about fusion now. So we already heard a little bit about fusion earlier. There was a question about this. So I want to define this. So I already defined the monoidal product. But you want to have a little bit more. So maybe first give you an idea of what a fusion category is. I'm not getting a precise definition. So I think the easiest thing to think about is you take a finite group, you get finite dimensional representations of this, and then you take two irreducible representations. You can take the dense product, and then we know well we can always decompose this. You can decompose this dense product into irreducible representations. So this tells us this Nijk. This tells us how often does this irreducible representation phi of k appear in this dense. Right, so that's an example of a semi-simple monoidal category. More structure here. Right, so for the Tory code, we can do simpler. We have defined these automorphisms, and we can compose them. And in this case, it's not too interesting. If you compose the row X with itself or the row Z with itself, you just get the identity back. So you see this most easily where you just they're both defined in the same string, right? Because the component makes it split the identity. Okay. And then the row Y one, so that's the electromagnetic one, is the combination of the vector one by definition. So so in this case, this is so-called a vegan theory, where always if you fuse, so this operation called fusion, if you fuse to of these anions, you always get with the sequence there. So maybe. But what I'm going to do is I want to explain this procedure in a sort of in a more general setting that we have with this superselection criteria. So for the Tory code, you don't really need that, but for the more general ones. So I have to say a little bit about the category. We already kind of used some of these things, but our category has a nice properties that all the set morphisms, they are vector spaces over C. It's easy to see if you need to find anything, sum of two interfiners, you get a look at it. We have a star operation, which in our case is just the star that comes from our algebra. So it does nothing on objects, and it sends B star. So if you have an interfiner, the star goes to the way. So I already used this in the definition of braiding. And in fact, what you can see is that the set of and the morphism from row to row is always a C star algebra with the normal. Right. We don't really need that structure here now, but the thing that I want to use from this that I can say when an intertwiner is an isometry or an orthogonal projection or a unitary. But this is really just means the same as if the intertwiner is part of operator, so it's the same property. But you can define this with an abstract vector. Right, so what are we going to do? Well, we're going to define, what does it actually mean, a direct sum of our endomorphisms, right? Because we want to decompose things into direct sums. So first I need to explain to you how to do that. And the other thing that we want to do is if we have some projection in this so in the binder from rho to itself, that's the projection. So you can think of representation theory, you have a projection onto an invariant subspace, that's the best what you think of. Then of course you want to be able to cut down this invariant subspace. These are the things you want to do. So for the expert so basically what I want to show is that delta DH are an additive category. It's not quite because we don't have a zero object, it's in our sense, setting that doesn't really make sense. Right, so before I can explain that, I have to tell you a little bit more for Neumann algebra theory. Neumann algebra is called a factor if it has a trivial, if the center of this thing is trivial. So you can show that any Neumann algebra you can sort of decompose into factors. But these are very useful. And this definition here, a trace or maybe a tracial weight, maybe a better name, on M is a linear map. The positive elements 0 to up to infinity, so it can be to infinity. But linear map, I really mean here that if I take the sum, trace of sum of elements is the sum. So this is the positive element, so it's not a linear space, but you get a multiply with the negative numbers. Right, so what I want is the property there as this one. So A star A is always a positive operator, it's not well, and I want that trace operator. And the other one is kind of so multiply with a positive number. Good. Right. So you can always find a trace that's non-zero. There's a very trivial one, then you take the one that so I should have said that's non-zero on projection. So you want to sort of the projection. You take a projection, you do it into an algebra, and you can always find a trace that's non-zero for projections. There's always a trivial one, namely you can define a trace that takes 0, 0, and infinity on all the other ones, all the rest of the thing. That's very interesting. But you can classify the factors in types of what kind of traces you can actually find. So for a factor of type 1n, you can find a trace such that the values of projections are up to scaling given by the integers, and this also might be an infinity. So this is sort of the easiest case of a Neumann algebra, namely if this is the case, your Neumann algebra is just P of H for some space H. So this thing is related to the dimension of H. Right. Slightly more interesting are the so-called type 1 factors. So in this case, I can find a trace that takes all the values. They can take all the values to 0. So it's really so all these. So when I say this interval here, I mean that all these values actually occur. All the values in the interval occur as traces. So in this case, it's actually you can actually take a thing. So type to infinity is quite similar. Only now it's the whole positive real numbers with infinity as well. And type 3, there are no interesting traces there. Right, so that's the classification of factors, and it's properly infinite. I mean, if in these ranges here, you have infinity simple things. Good. So that's another way of classifying factors just in terms of properties for the axes. Right. I want to use this to define direct sums. So if I have two objects in delta DHR and I can find two partial isometries such that their range is sum of the identity, then I can find a new object like this in this way. B1 row 1A, B1 star plus B2 row 2A star. So really what I'm doing is I have my own space, I cut it up into different pieces, and I just take one to the first piece. That's really good. Right, so this is again a representation, so you can easily check that. You multiply this, you can use this property. Right. Good. So for the Torah code, this is a lemma. You can see that actually these coding algebras we looked at is a so-called type 2-1 vector. This means it's properly infinite, and the property of the properly infinite vectors is that I can find such isometries in there. So I can find for a given cone, I can find these two isometries that simply the identity. Sorry, this should be yes, so there are so and then from this it follows that delta D are as direct sums. So what you do, you have something that's localized in this cone, you choose these things that are also in the cone, and then you check that this is again localized in the same cone, just like the computation. So you're outside of the cone, and this will commute with this one, and by locality, and you can take this out of the case. So that's a way to define direct sums, and it really needs you really need to be able to find these. So a general property of these direct sums is that's maybe obvious from this description, but they're unique up to unitary units.
Or is the point that there are infinite direct sums? Because that's all additive categories have finite.
Sorry?
Is the point infinite direct sums?
You can have infinite direct sums.
Because additive category has finite direct sums. Or is it just defining what
so yeah, so I think you can do this fine many times, sure. So infinite direct sums is a bit more tricky, and they will have properties that we don't want. I will come to that later. But yeah, this is for now we just consider finite direct sums. I mean, if you really want to end up in with a fusion category, model tensor category, and these by definition they are finite with they have the finite. Right. So that's direct sums. Now I want to go the opposite way. So let's say an orthogonal projection. I want to sort of restrict to this invariant subspace. And you can do that if you have a V. Right, so this is the definition of a direct sum, which is that we define the sigma rho that is partial isometry with this P as a range projection. So if you can do that, this sigma is so it's really restricting the values. And again, we can do this, so you can prove under quite general conditions that if you have an intertwiner like this, as a projection, then you can find some isometry in this cone with VB star. So you're not quite sure. So I think you actually need to use a slightly bigger cone, but that is really important because you can always press it first in a smaller cone. Then I think this should be slightly bigger cone than the representation. That's important. But yeah, so using this, you can show that we have sub-objects, and this is fine. Again, it's an easy check that this is localized and transportable when it's displayed. So let's bring it together. So if you have this, well, by definition, as you would expect, these if you take the direct sum like this, then this row 1 and row 2 are sub-objects in the way it is defined. And if you have a non-trivial projection, you can get sub-objects from well, row 1 and row 2 corresponding to this projection and the component projection. And so if you have a non-trivial projection, you can decompose row as a direct sum. Well, right. Good. well, this is of course definition that you all know. We call an object in delta D representation irreducible simple if and only if the homomorphisms intertwined between these things are. But this is just to say that it's just really saying the representation is irreducible. Good. So now I want to obtain the fusion rules. So if you take two irreducible objects and you want to know, can we actually decompose it in this way? So from the general theory that we have so far, the answer is well, we don't know yet. It's not guaranteed. There can two things can actually happen, both interesting in their own right. So the first one, it could be that maybe not maybe not finitely many irreducible sectors. There might be infinitely many irreducible sectors. So in this case, that's not too much of a problem. But the other thing that can happen is that actually, if you take this, if you take a projection, we can always decompose this tangent product into direct sum of these two things, and now then look at the projections over there and try to decompose these things further. But there's no guarantee that this procedure will end after finite both steps. So it might be that the object is like an infinite direct sum, or maybe even a direct integral. So this is related to the goal to be interview. So yeah, so that's not guaranteed from our setup that is finite. It doesn't really matter because you can still
What does sector mean? Does it mean simple objects?
Sorry, is there a question?
What does a sector mean? Does it mean simple object?
The air conditioning is broken in my ear, so I'm afraid I cannot really hear the question very well.
Question is, what does a sector mean? Does it mean simple objects?
Oh yeah, sorry, yeah. So yeah, I mean, yeah, so really say irreducible sectors. Yeah, sorry. And thanks for the yeah, so simple irreducible, yes.
Thank you.
Yes, I use this terminology not really consistent. So but yeah, in this case, I mean the irreducible ones, yes. Thank you for the question. Good. Right, so but in the Torah code, that's not going to be a problem. As I said, we always have this finite this thing here. So I'm really trying to wrap up soon because we talked almost an hour. I should maybe say that these in the Torah code, so we go back to the Torah code, that if I take two excitations of the x type, so with the infinite string, I take a fusion product, and I look at this in the ground state, you basically get a state with two excitations. But this is in the trivial set. So I mean, I have a picture of this. So if I look at this state, so this is the ground state. I have two of these x-type strings that go into infinity, and this state is really the same as this state, with some path connecting these. So if I fuse these two things, I end up with a state that has these two excitations, but this is in the ground state sector because I can get rid of these excitations by just with the finite with the local operator, maybe besides this part. So this is kind of related to this question that we had earlier about the ground states of the Torah code. Right. So yeah. So it's not right to say that if you fuse these two things that you get a trivial state with no excitations, but you get something in the trivial sector. So that so in the Torah code, the excitations will be 0, 1, or 2. Good. So let me make some remarks. So the existence of direct sub-objects follows from quite general assumptions. So in the Torah code, we know exactly what this cone algebra is, but you can show that these isometries they exist quite generally. Namely, if you take a pure ground state, they bounded finite range interactions. satisfying certain gap condition. That's very similar to one that Bruno wrote down earlier. Then you have that's the result by Chico Gata. So yeah, so another thing that's maybe of interest is you can look at these cone algebras, and I mentioned for the Topological code like to infinity. But you can also construct models using stringnet, stringnet models. You can construct models where the cone algebras is type 3. And you can even provide a final classification for those who don't know about this kind of thing. But the interesting thing is that you can actually define models that have the same superselection structure, but they have different types of code algebra. So it's really the style of this algebra. It's more of a artifact of how you define the model than really physical variables. So yeah, that was quite surprising when I found it out. Maybe finally, the last thing that I want to say is that if the dimension of this irreducible, if you take some second or some representation of rho in a category, and the dimension of the finite is finite dimensional, then you can always decompose it into irreducibles. In this case, it's the finite dimensional algebra, so you just take the minimal projectors in there. And that will give you the decomposition. Right. So maybe say a little bit more about this tomorrow, but this is very much related to what's called the rigidity of the category. So if you have duals, if you have duals, then this is automatic. Right. Yeah. So further structure, I think that's a good moment to stop. So let me postpone this to tomorrow. And yeah, stopping. Thanks.